And the very first theorem will be the Gauss Divergence Theorem, which we are going to start today under the heading of vector calculus. So straight away let us start the theorem, and the name of the theorem is Gauss Divergence Theorem of vector calculus. And let us state this term. If f is a vector point function having a continuous first order partial derivative, this is the statement, in the region V, this is the region V, bounded by a closed surface S. So then the triple integral over V, there will be divergence. Del dot f means divergence of f vector is equal to the surface integral f dot n cap ds. And you know what is the meaning of n cap. This was discussed in the few classes back. N cap is a unit vector which is normal to a surface. Suppose we have this surface S, and this is the unit normal vector along the side normal to the surface at this point. So this is your n cap, and ds we shall select according to the statement. You know that how to select a ds. ds, if we are selecting, if we are in xy plane, then we shall take like this. This was discussed in the previous classes. We can select ds in 3 ways, and this will depend upon according to the statement of the question, that how to select and what to select ds. You will select dy dz, you will take I cap dot n cap. If we select dx dz, you will take j dat and j cap dot n cap. So these are the 3 ways to select ds. So now just see, this is left hand side, this is the divergence of f vector, and this is right hand side, this is f dot n cap ds and double integral. So this is the statement of the theorem, and we shall apply the theorem now. The question may come in 2 types. Suppose the first type we are going to do, that we have to verify Gauss Divergence Theorem. This is the first type which we are going to do. In the first type, if the question comes like this, you have to find left hand side and right hand side both. You have to calculate left hand side and right hand side and check whether the values are equal. The values should be equal. This is our first type, that we have to find a triple integral and surface integral, and both should be same. This is our first work. Now the question is, the vector f is given to us, that is x square I cap plus z j cap plus y z k cap. This is the vector point function taken over the cube bounded by the planes. These are the planes given to us. These are the equations of planes. This is the cube actually. Do you know that cube is a 3-dimensional figure that will be taken as just like a room, and we will take like this. This is the square we have, and similarly we have this square. So you can take, this is the y-axis, you can connect these sides. So this is the cube we have, and okay, the axis should not be like this. This axis should not be taken here, it should be taken this one. I think the figure is a little tilting from my side. You please plot a straight figure. This is the z-axis we are taking. This is the x-axis we are taking. This type of question have already been done in the previous class. On the parallel side, we have to evaluate. So we are going to name the sides. This is a C dash, this is B dash, this is A dash, this is P dash, this is we are going to take, this is a C, and this is a B. So all the surfaces have been named. You know that along x-axis we have I cap vector, along y-axis we have j cap, and along z-axis we have unit vector k cap. And you all know x0, x1. x0 is at O point, that is origin point, and x is equal to 1 will be on x-axis. This is x-axis. So it is clearly 1, 0, 0. It is clearly 0, 1, 0, and it is clearly 0, 0, 1. So by this way you can also find out the coordinates of other points also. And if I cap is on this side, then negative of I cap will be on the other side of x-axis. Similarly, if j cap is on this side, and then j cap negative will be on the opposite side of this axis. So we know that for evaluating or for verifying the divergence theorem, we should evaluate this triple integral over the divergence of f, that is a surface integral f dot n cap ds over s. So name it as equation number 1, and we need to evaluate this equation and find out that both sides are same. So let us take the faces we have. We have a first face. The name of first face we are going to take, that is OAC dash B, and it is clear OAC dash B. This is your S1 face. Actually, this is the floor of the face which we are going to take. And you know that if we want to evaluate the right hand side, okay, wait a minute, name all the faces. The S2 face we are going to name, that is a C, B dash. We are going to take, that is a C. This is a C dash actually. This is C dash, B dash, P dash, A dash. This is S3. We are going to take OB. This is OB, A, and C. And this should not be OBAC, and S4 we are going to take, that is BC A dash P dash, this roof. S5 we are going to take, that is OB dash, this one, OB dash A dash and C. And S6 is left here, that is what is left with us, that is BCP dash A dash has already been taken, this has already been taken, OAC dash B is taken, OABC is taken, and OB dash, this is OB dash and A dash and C. This is your S6. So 6 faces are there in this figure, and it means the right hand side, the surface integral f dot n cap ds is divided into 6 faces, over S1, over S2, and the third face is over S3, over S3, this is S4, This is S5 plus S6. So you need to evaluate all the integrals along 6 faces. So and then add up for finding out the right hand side. In this question, left hand side is easier to find, and this is likely to find surface integral. That's why I am going to find surface integral earlier. So over S1, and what is S1? OAC dash B. This is the face we have. This is the flow actually, and it is clear. This is along z-axis, and it is on the other side. So n cap, your unit vector will be negative of that, and this is in xy plane, xoy plane, and in xoy plane it is clear that z will be 0. So what does it mean? This means ds should be dx dy over a cap dot n cap, and there will be dx dy, because in the denominator we have to take modulus, so that come out to be 1. So the double integral f dot n, this is n vector, and what is f vector? Dot product of k will be k dot k will be 1 only. So f dot n cap ds over s1 will be minus of yz into dx dy, and it is a yz, but z is 0, so this come out to be 0. So the second one is over S2, and what is S2? That is C dash B dash P dash A dash, C dash B dash P dash A dash, and this is along the y-axis, so n cap will be equal to j cap, and in that case what we should have, f dot n cap ds over s2, j dot j is 1 always, so z j cap means z, and what should be ds, because this is along this is the face which is lying in x over z plane. So we shall find out ds is equal to dx dz over n cap dot j cap. So ultimately dx dz will be there. Limits are clear, 0 to 1, 0 to 1. You just see the planes bounded. These are the limits given to us. x0, x1, y0, y1, z0, z1. So now you can evaluate over S2, integrate it, but it come out to be z square by 2, 0 to 1, and the dx integration is 0 to 1. So ultimately this is 1 by 2. So over S2, the integration is come out to be 1 by 2. Now let us find out over S3 now. So what is S3? That is OBAC. This is OBAC. This is XOZ plane, and that will be equal to negative of OABC, we can say, and n cap will be equal to negative of j cap, and f dot n cap will come out to be negative z, and that will again be dx dz, and there will be 0 to 1, 0 to 1. So ultimately it come out to be minus 1 by 2 on the other side of that. Now over S4, and let us see what is S4. That is BC A dash P dash, and for BC A dash BC A dash, this is BC A dash P dash. This is the face along z axis actually, and z is equal to 1 in this side. So z is equal to 1 and n cap is equal to k cap. What we should have, This is a double integral over the surface S4 f dot n cap ds will come out to be n cap dot k cap, and what is that will be yz, and we have already taken along s1. This is just opposite to that, so that should be dx dy, but z is 1 here, so you need to put z is equal to 1, so y dx dy is there. Limits are 0 to 1, 0 to 1. So y square by 2 given the integral 0 to 1, and this is integral 0 to 1. This is 1 by 2. So over S4 the integration come out to be 1 by 2. Now let us find out over S5, and let us check what is the phase S5 we have. It is moving very slowly. Yes. Okay. This is the phase we have S5. Okay, this is the phase S5, O, B dash, A dash and C. O, B dash, A dash and C, and this is Y, O, Z plane. In Y, O, Z plane, clearly n cap will be equal to negative I cap, and x will be 0. So x will be 0 in this case, and n cap will be equal to negative I cap. And your double integral will be with I cap, and this come out to minus x square, and you will find out dx will be dy dz, and in the denominator n cap dot I cap, so that will be dy dz, but x is 0, so this come out to be 0. Now the last phase is left with us, that is S6, and the coordinates are A, B dash, P, C dash, and for this phase n cap is equal to I cap and x is equal to 1, and your integration will come out to be x square into dy dz, because the phase lies in y or z plane, and put x equal to 1 here. So when you put x equal to 1, it will become 1. So ultimately we should have integration of dy is y and integration of dz is z. So you will get 1 in this case. So by adding all the phases, we should be able to find out the value of the surface integral, and let us see what is the surface integral. The sum of all the phases. Over S1 it is 0, and over S2 it comes out to be 1 by 2, and over S3 it is minus 1 by 2. It will add up to 0. Or over S4 this is 1 by 2, S5 this is 0, and over S6 this is 1. So the sum total of the surface integral come out to be 3 by 2. So the right hand side mean the surface integral f dot n cap ds over the total surface S come out to be 3 by 2. Now let us check whether the divergence of the volume integral should also come out to be 3 by 2, but it should come out. So the divergence with the f vector del dot f, you know that what is the del operator we have. Del operator is this: I cap del by del x, j cap del by del y, k cap del by del z, and it is a dot product with f vector, and f vector is x square. This is x square I cap plus z g cap plus y z k cap. So let us operate the dot product. I dot I is 1 and del by del x of x square is 2x plus derivative of z with respect to y is 0 and derivative of this with respect to z is y. So ultimately it come out to be 2x plus y over the volume integral dv, and dv is dx, dy, dz. But we have all the limits 0 to 1. So you just need to evaluate this, and let us integrate with respect to x. If you integrate it with respect to x, you get 2x square over 2 plus xy within the limits 0 to 1. So 0 to 1, 0 to 1 is left with us. Now this 2 will be cancelled, and when you put the limit, after substituting the limit, it comes out to be 1 plus y. This is dy dz. And now you know that we have to integrate with respect to y now. So that is y plus y square upon 2, 0 to 1, that is dz. And substitute the upper limit y, it comes out to be 3 by 2 into dz. And lower limit, for lower limit, the value comes out to be 0. So ultimately, this comes out to be 3 by 2, and the integration of dz in z within the limits 0 to 1. So this comes out to be 3 by 2 also. So left hand side and right hand side have same values. It means the Gauss Divergence Theorem is verified. So this is the procedure to verify Gauss Divergence Theorem. That you have to evaluate surface integral and you have to evaluate volume integral, and both sides should be same. And the question in final exam may come like this: that verify Gauss Divergence Theorem. It means you need to calculate both sides, volume integral and surface integral. This is one type. One more type of the question comes like this. Suppose the question comes like that: use a Gauss Divergence Theorem to calculate. Let me take the question. Okay. Use Gauss Divergence Theorem to calculate the surface integral f dot n cap ds. One more thing is there. The surface integral is written in two ways. This is first way. We can also write down surface integral like this: f dot ds. This is the another way. Both have same meaning. There is no difference as such. Now, what is given? F vector is given to us, that is x I cap, x cube I cap, y cube j cap, z cube k cap, and s is the surface of the sphere. X square plus y square plus z square is equal to a square. This is the sphere given to us, and it is a very important question. So you have to evaluate this, but you have to use Gauss Divergence Theorem. So by divergence theorem, what divergence theorem says, that the surface integral is always equal to volume integral, and the volume integral is del dot f dv over v. This is by divergence theorem. It means if you want to use divergence theorem, then you need to evaluate the volume integral. And we have to compute this, but both have same values. So that's why we need to compute volume integral in this case only. Only volume integral will be computed. And let us see. This is very important question. The volume integral, that will be divergence f. So divergence of this will be 3x square, 3y square, 3z square, and dv is clear, that is dx, dy, dz. This is there. Now, it can also be written like this. 3 can be taken common, that is the triple integral x square plus y square plus z square dx, dy, dz over v. Now, because the sphere is given to us, so you will use spherical polar coordinates. Changing into spherical polar coordinates. So, for changing into, what is this? This is given in x, y, z. X, y, z are Cartesian coordinates here. So Cartesian will be changed to spherical polar under making substitution, and substitution is put x is equal to r sine theta cos phi. This is a standard substitution. You have to remember y is r sine theta sine phi, and z is equal to r cos of phi. This is the spherical polar coordinates, and also you have dx, dy, dz, and dx, dy, dz is Jacobian modulus of dr, d theta, d phi. This is the formula actually to find out this volume term. And what is this? This is actually dv. You know that we have substituted in place of dv. So you need to evaluate j modulus. Modulus means positive value we need to take. So let us compute j. What is j? Derivative of x with respect to r, derivative of x with respect to theta, derivative of x with respect to phi, derivative of y with respect to r, derivative of y with respect to theta, derivative of y with respect to phi. So derivative of z with respect to r, with respect to theta, with respect to phi. Now this is the Jacobian which we need to compute. So put the values of the derivative. First derivative of x with respect to r, that come out to be sine theta cos phi. This is r cos of theta cos of phi, and this come out to be minus r sine theta sine phi. And this will be a determinant of order 3. Derivative of y with respect to r, that is sine theta sine phi, r cos theta sine phi, and the next one will be r sine theta cos phi, finding out the derivative. Similarly here, cos of phi, that will be 0, and that will be minus r sine phi. So ultimately its value, when you expand that, when you expand this three-dimensional determinant, you will have the value r square, नहीं क्लास चल रही, r square sine theta. This is the determinant we shall get after expanding this. So you will put the value here. This is r square sine theta, and it is the standard value. This will always be same in case of spherical polar coordinates. So in each of the question you will do this step, and this step will be similar always. There will be no change. So one more thing. What are the volume region of integration? This is called V. V is the volume or the region of integration r theta phi, in which we shall write down the limits. The limits of r are 0 to radius. Radius of the sphere is a, and because these are the spherical polar coordinate. Theta is from 0 to pi and phi is from 0 to 2 pi. These limits will always be same. There is no change in these limits. These are standard limits. So let us conclude. Therefore, the surface integral f dot m cap ds over s will be equal to 3 is common, and we shall substitute the limits 0 to a, 0 to theta, and sorry, this is a 0 to pi. The limits of theta is 0 to pi and limits of phi is 0 to 2 pi, and this is a square into sorry, not a square here. We shall substitute r square first. So this is r square, and the value of the Jacobian is r square sine theta dr d theta d phi. This one. So we shall substitute this value. Now let us integrate separately. R square is R4. So R4 over 4, because all the three integrals are independent of each other. Integration of sine theta is minus cos theta with the limits 0 to pi, and phi is a single, that is 0 to 2 pi. So ultimately, after substituting the values, it comes out to be 12 pi a5 over 5. So this is your required value of the surface integral. So this is the procedure to find out the one side of the integral by applying divergence theorem. So this is all about the divergence theorem. We shall continue in the next class with the Green's theorem and try to compute the or verify the theorem. And one more theorem is also left with us, that is the Stokes theorem. So thank you very much.